technologies industry for mobile systems, communication systems, and data centers, what we come up with is, or there's estimates that show that the aggregate impact is 1.2 to 2.2 billion metric tons of CO2. This is anywhere from 2 to 4% of worldwide emissions. And I know a lot of us come from a quantitative background, and so you're probably looking at this and you're seeing, well, that's 100% error rate potentially, or like a range. That's right. It's a really wide range here, partly because it's so hard to quantify this, and there's such a lack of data in this space, and that's one of the first things that we're going to be talking about as well. But regardless of whether it's 2% or 4%, it's already a lot. In fact, if you aggregate all of computing technologies, it's more than a lot of countries worldwide. Not only that, it's actually on par with the entire aviation industry's footprint. So I don't know how many people do this, but like if you go on Google Flights, you can see what the carbon footprint of taking a flight from like New York to California, New York to Paris. I'm going to be flying from New York to Brussels soon, so I can actually see the carbon footprint of that, and it's very front and center for everybody. Computing is not like that, right? We don't typically think about, oh, I just bought a mobile phone, I just bought a laptop, I'm using ChatGPT or Gemini or Claude. What is the environmental impact here, right? Like a lot of people are using the note takers. What is the environmental impact of these note takers? I'd argue probably pretty high. Finally, these emissions are actually expected to grow quite rapidly over the next 5 to 10 years. There's a lot of reasons for this. One, obviously, like we've heard a lot about how data centers are expanding and the capacity of data centers is continuing to grow because of the demand for AI. Not only that, the number of mobile devices, the number of people that are using the internet is increasing worldwide. And finally, the amount of compute our applications are taking, our workloads are taking, is also growing at a rapid rate. Okay, not only does computing have a carbon footprint, but you can also think about the environmental impact of computing from a water perspective. When you think about water, there's a couple of aspects of water that I want you to remember. The first is water that's used to actually generate the power itself. So whether you're using hydropower, even some forms of kind of natural gas and so on, they need cooling towers, they need even nuclear power plants, right? Like they need some cooling towers, they need access to water. So that is one source of water consumption. The second source of water consumption, which we call actually scope 1 at the top of this figure, is water to cool the servers that we're actually using. So especially as we get to more and more sophisticated applications, such as AI, right? We are going to be running these processors that require a ton of energy, a ton of power. They generate so much heat that we can't just cool them with air anymore. We're going to need to cool them with water, with active cooling mechanisms with water. And so that actually consumes a lot of water consumption as well. So this is some data that I pulled together. There's actually a lot of stats like this that you can find. There's a lot of emerging data. This is one that I thought was particularly kind of put it into context, at least for me, right? So this says data centers rank among the top 10 water-consuming commercial industries in the U.S., right? That's kind of crazy to think about in terms of like in all industries, right? Like data centers are already top 10. About a quarter of this is due to direct cooling, right? So if we go back to the previous slide, I talked about how we need water to be able to cool our chips, right? That's only going to continue to increase when we talk about AI, because we have these really, really sophisticated processors that are going to be generating so much heat that need to get cooled more and more. And so that quarter factor of using water for direct cooling is going to continue to grow as well. There's some other papers that talk about actually a typical kind of ChatGPT query using GPT-4 consumes almost the same amount of water as like half a bottle, right? That's a lot of water that we're talking about. And depending on which paper you're reading, depending on which company you're talking to, sometimes these vary. I'm not going to really comment on like which company is right or wrong. There's different methodologies, and that's part of the hurdle over here as well. But let's look at the scale of some of these data centers that we're talking about, right? Like when we talk about AI, it's typically at the data center scale. And so this is 6 of the major kind of data center operators. So Amazon, Google, Microsoft, Meta are the kind of predominant hyperscalers that we think about. Digital Realty and Equinox are the co-location. So if you have multiple companies that are sharing one data center, that's what we call a co-located data center. As a frame of reference, we have New York City on the right side. That's the annual electricity consumption of New York City. So if you imagine adding up all of these data center operators, stacking those bars together, it's going to be significantly higher than New York City, which is in itself quite large. Most of these data centers, if you look at, say, Google and Meta, over 75% of this capacity is actually in the United States. On top of this, they're growing at a very fast pace. So 25% CAGR. CAGR stands for cumulative annual growth rate, which means year after year, Amazon, Google, Microsoft, and Meta are consuming 25% more energy. This is pre-generative AI. I don't have the numbers yet for how the boom of like generative AI and the data center expansion that we've heard of over the last 2 years is going to be impacting these numbers. This is already a lot. Okay, let's put this in the context of renewable energy, right? So when we think about sustainability, we think a lot about renewable energy as well. So renewable energy in the United States is growing at a rate of 7%. Now, the absolute amount of renewable energy is obviously a lot higher than the absolute amount of energy that's going into data centers. However, in terms of new renewable energy capacity that's coming onto the grid, nearly half of that capacity is going to data centers. And so when we think about sustainability, this becomes a really interesting equity question for different communities, right? These data center operators have so many resources, so much money, to be frank, right? That they can procure more renewable energy than maybe our local homes and residences or smaller players as well. And so this becomes an interesting question in terms of, well, yes, the technology industry has been procuring more and more renewable energy. That doesn't mean that our society at large is getting more sustainable. Oops. So the good news, if you kind of rewind the clock at least like 3 years ago, was that around 2020s, a lot of these big tech companies were making these pledges to be carbon neutral by 2030, by 2040. This is almost every single major technology company across the ecosystem, including Apple, TSMC, and on the fabrication side, Facebook, Microsoft, Google, Amazon, all had these pledges. Now, what they meant in terms of achieving these goals, what goals they set up for themselves was different. Some of them talked about net neutrality across their supply chain. Some of them talked about getting a significant amount of renewable energy to power their data centers and operations. But they all had these pledges. Unfortunately, what kind of happened after these pledges were made was AI. Right. So when we talk about ChatGPT, when we talk about generative AI, what these companies didn't anticipate after 2020 was that there was going to be this massive explosion in demand in compute and AI, that they would need to build so many more data centers. And so these are two Bloomberg articles, one about Google, one about Microsoft, telling the same story, which is both of these companies are no longer going to be able to meet their carbon neutral pledges by 2030. And they both have kind of these charts that are taken directly from the sustainability reports from the companies, which show the gray dots that you're seeing that are going down was the anticipated or the goal of these companies to get to zero carbon emissions or zero net carbon emissions. But instead, they're kind of seeing these black dots that are going up because of the new capacity and all the demand for AI. You've seen articles like this as well, probably, right? A lot of these companies are going to, Microsoft, I think it was reviving 3 Mile Island, right? A lot of these companies are trying to look at new power sources, looking at nuclear power, building their own capacity, building their own kind of power sources for data centers. There's also articles and discussions of how a lot of tech CEOs are going to the federal government, trying to get access to more power, trying to get onto the power grid. It's actually one of the biggest challenges right now for the power grid. They haven't seen this rapid intensity of demand happen so quickly before, and they're not able to keep up. And so a lot of these power grids are actually having to go back to data centers and say, look, we can't bring on this amount of capacity at the rate that you want. You're also seeing reports of local communities reporting that nearly like 40-50% of all of the energy that's being produced or being available on the grid for those local grids is actually going to the data centers. This can create real challenges for local communities as well. So when we think about sustainability, it's not just a global problem, it's also a local challenge that different communities are going to have to deal with in different ways. Okay, so what does our lab do in this space? Well, we call ourselves S4AI, which stands for Scalable, Sustainable, Specialized Systems for AI. A lot of the work that we do is around sustainability. And we focus on 4 main areas. One is carbon accounting and reporting. So how do we quantify the amount of environmental impact? And I'll focus mostly on carbon. We do a little bit of stuff in water and e-waste, and we want to get into those spaces more. But right now we've been focused on carbon. We do a lot of design optimization, both at the software and the hardware layer. Education and workforce development, so I teach a class here at Cornell Tech on sustainable computing. And we host a lot of workshops. We talk to companies about how do we upskill talent in the sustainability space. And then economics and policy. Arguably, the most impactful thing that we can do is have good economics and policy that motivate companies and motivate stakeholders to care about sustainability. Okay, so what I'm going to talk about today, the meat of this presentation is going to be on 3 topics: understanding the hidden cost of computing from a carbon perspective, designing carbon-aware AI systems, and then a path forward. If there's one thing I want you to take away from today, if you don't remember anything else, it's the term life cycles. When we think about sustainability, always remember life cycles. If you want to understand what is the environmental impact of any system, you have to know where was it designed or built or implemented, how it was deployed or used, and if it's kind of recycled or reused in any sense, what is the impact of that? So maybe we've been talking a lot about AI and folks here have been thinking a lot about AI, so we can think about the machine learning lifecycle as well, right? So this is a pie chart of data that we gathered at Meta in terms of what is the environmental impact of different phases of the machine learning lifecycle. So when we think about the machine learning lifecycle, it's training, inference, and then gathering the data, right? So when we started out to do this work, a lot of attention when we talk about environmental impact of AI is around training and experimentation, because those are the big kind of compute engines that we need, right? Like we need all the GPUs to train these massive, massive trillion parameter models. In reality, at a company like Meta, only about 1/3 of the environmental footprint is around training and experimentation. The remaining almost 70% is split across data collection and storage and curating data sets, and then actually deploying these models to do inference, to do useful work. So this is to say that we can't just focus on any one piece. We really need to think about all pieces of the puzzle. Now this might vary for different use cases, right? Like if you're taking a pre-trained model off the shelf, and you're just doing a little bit of fine tuning and then you're going to use it for years and years after that, maybe your inference cost is going to be a lot higher than your training and your data collection cost. You might also have opposite situations where your data collection cost is very, very high, but your training and the inference cost after that is very low. You can apply the same concept of life cycles to hardware systems as well. So when we think about hardware life cycles, we have 4 phases: manufacturing, transport, product use, and then recycling. Now as CS majors, when we think about product use, that's all about how much energy goes into actually running our systems, right? So a data center is how much power goes into the data center. For your mobile phone is how much you have to charge your mobile phone, right? Most of our CS education and our computer engineering education is all around this phase. How do we make processors faster, more power efficient, more energy efficient? The other part that's going to be really important is this manufacturing aspect. So where do we actually fabricate our chips? How do we build our systems, right? That's also going to have a really high environmental cost. If you come from the data center realm, sometimes we talk about this as CapEx, or capital infrastructure cost, and then OpEx for operating costs. So just as an example, this is data from Apple's corporate sustainability report. So I'm just taking their report and I'm overlaying the life cycle emissions on top of it. And what we see is nearly 75%, or 3/4 of Apple's emissions are coming from manufacturing their devices. That's the portion in red that you're seeing. The green portion, which is actually using the devices, all of our phones and watches and laptops, all of that, is about 19%, right? So about a fifth goes into actually charging the devices. They apparently have a way to track this and average it over all of their users. Not terribly surprising, I guess. The blue portion is product transport, right? So actually shipping us all the devices so that we can hold them in our hands. Recycling is a little sliver that you actually probably can't even tell unless you're like very, very close to your screen right now. The gray portion is business travel. So I like to think about that as the human part of Apple, which is actually all the people doing the stuff and the offices and all of that. As a computer architect, right, so Neeti mentioned that I'm a computer architecture researcher, we can actually go a little bit deeper into this, right? So if you look at the different pieces of the manufacturing cost, the biggest portion comes from integrated circuits. So think about Intel fabricating your chips, think about TSMC fabricating your chips, Micron, Hynix, Samsung, right? These are processors, these are memory chips, these are storage chips. Fabricating them has a huge, huge cost. Another way to think about this is the moment that you buy your phone, like this phone over here, you as a consumer have already had the environmental impact of 3/4 of the entire lifetime of that device. Okay, well this is general data across the entire company. What if we're a system designer, a mobile system designer, and we want to actually optimize one of these devices? Well, how do I actually go about that? Well, the first thing is we need to have tools to be able to actually measure and quantify the environmental impact. I won't go into a lot of the details here, but current methods of doing this fall into 2 categories. One is called EIO, or economic input output, which basically says how much did you spend on that service or that item, and there's a ratio factor that takes dollars to carbon. This works at nation state levels, this works at industry levels, right? Like comparing computing to agriculture maybe. This doesn't work for iPhone 16 to iPhone 15. I actually don't know which ones are the most recent. The other category is called lifecycle analysis. So this is where if you wanted to have a very detailed report, you would go to a consulting firm. They would have a giant database of all components, like all the way from the plastics to the aluminums to the different materials. They'd go through this painstaking process of tracking how all the minerals for that device were gathered, where it was manufactured, where it was fabricated, and then how you're going to use it across the entire lifetime. These databases are typically very outdated. They're using 45 nanometer technology, which if that doesn't mean anything to you, that's basically processors that were probably designed 15 years ago. And these LCAs take a really long time to conduct. When I was at Meta and I was working with some of the consulting firms, this would take us nearly 6 months to get an answer back for one device. And they're also very costly, tens of thousands, hundreds of thousands of dollars for one of these devices. one of the first things that our lab has been working on is developing tools to make this process as easy and as quick as possible, especially for the integrated circuits, because that's our area of expertise. I won't go into a ton of the details, but we effectively designed this tool called ACT. I wanted to be very proactive. And so we called it ACT, Architectural Carbon Modeling Tools, which takes as input characteristics of your workloads or the applications that you're running on your hardware system, how the chip was designed, what is the area, what is the technology that you're using, which fab it was fabricated in, like Intel or TSMC, and where that fab is located, right? Like, is it in Arizona, is it in Oregon, is it in Taiwan, where is it? And then, whoops, out pops the operational and the embodied carbon footprint of that system. And then once we have that data, we can then close the loop and then do this carbon-aware hardware optimization. If folks are interested, I can definitely share the paper on this that has a lot of details of how we do this modeling, and it's built on a lot of device data from actually folks that fabricate these systems in industry. And so we kind of talk to them, we read their papers, and we basically fill in the holes as much as possible. While I was at Meta, before joining Cornell, we actually took this tool and I implemented it internally for Meta to be able to model all of the carbon footprint from the digital assets inside the data center. As of the 2023 sustainability report, they actually have a shout out to the methodology that they used, which points to different models that are being used for this carbon footprint analysis. If you click on the models, it goes to the open source version of ACT. So these things are actually being used by industry. I've anecdotally heard from other companies that they're developing similar methodologies, looking at ACT and looking at similar things that we've been doing. Now, one of the things that's really hard in this space is you have to understand the supply chain. And supply chain for computing is changing constantly. It's really wide. You have chips from different partners, from different companies. You have to integrate them. You don't know all the information. The Google Sustainability Report had this excerpt that says, uncertainty is inherent to most greenhouse gas accounting methodologies and results. And understanding the sources, types, and magnitude of uncertainty is crucial to deploying conservative estimates. So we also see this in peer-reviewed literature. So these are two papers. The first one that you're seeing in the center of the screen basically looked at storage devices and looked at the spread of the carbon estimates for them. And we saw that there's almost a 4x spread. And then the second paper that you're seeing is from the same group, measuring the same process. They had two different methodologies in 2020 and 2023, and they had nearly a 50% increase in the carbon footprint for certain technologies. These are really hard things to get right, and the estimates are changing, and there's a lot of uncertainty around the data as well. So what we've been working on is, can we model this uncertainty inherent in the design process to be able to make more robust decisions? So one of my students basically looked at the models that we had developed and tried to understand where is the uncertainty coming from, which parameters are the most prone to the uncertainty, and look at the supply chain data of what are the distributions that we are dealing with, and basically update our estimates to be more probabilistic. So instead of a point value, we get this probability distribution. And now we can tell designers, okay, with 95% confidence, we know that the carbon estimate of this system is this amount. Okay, so that's the carbon accounting. And okay, I'll try to go a little bit faster for the next part. But the next part that I want to talk about is, now that we understand how to actually quantify carbon footprint, what do we do with this data and how do we design more sustainable systems? And I'll use AI inference as a driving use case here, but you can do this with a lot of other types of systems as well. So going back to the hardware lifecycle of AI inference systems, we basically took our ACT tools and kind of ACT++ that we've been building on top of, and we applied it to state-of-the-art GPUs that people are doing AI inference with, right? So these are like NVIDIA GPUs, state-of-the-art, A100s, H100s, very frequently used in data centers. And what we did was try to look at what is the operational versus embodied carbon cost of the host systems, which are the CPUs and the motherboards, and then the GPUs that are actually doing the AI inferences. You don't really need to look at the data too much. The key takeaway is that the host systems, which are the CPUs, the memory, the storage, the networking, account for a majority of the embodied carbon, the manufacturing emissions. Whereas GPUs and these AI accelerators that are actually doing the work for AI account for a majority of the operational emissions, all the energy that's being consumed. And what this basically means is maybe if you want to have a more sustainable system, you want to focus on energy efficiency for GPUs and AI accelerators, but you want to focus on manufacturing efficiency or amortizing these embodied carbon emissions for the host systems. So how do we do this? We go back to the tenets of environmental design and we apply them to LLM inference. So the first one is reduce. So how do we come up with more efficient AI hardware systems, right? So reduce the amount of memory that you need, reduce the amount of storage that you need, reduce the amount of the complexity of the GPU that you're using. The second is reuse, right? So a lot of times in data centers, when we talk to data center operators, what we find is that their GPUs are being used. They have good utilization, like 60, 70, 80% of the time they're actually doing work. The CPUs are just sitting there. They're not doing anything. We're talking about like 6% utilization. So 6% of the time they're doing something useful. 94% of the time they're just humming around. And so can we do something that is useful with these idle resources? That's reuse. Recycling, how long should we keep these systems around in the data center, right? Especially for GPUs, when NVIDIA keeps putting out new and new hardware platforms year after year, there's a lot of pressure from companies to renew their hardware fleet. That's really bad from a sustainability perspective because you're paying this upfront cost for manufacturing these new servers. And then finally is right sizing. You can think about that as, depending on the complexity of your workload, can I find the right hardware platform that has just enough resources and no more to be able to perform the task? That can actually be a really challenging problem in data centers when there's so many different queries, so many different services that are running, and there's limited but also heterogeneous or diverse hardware platforms. Okay, I'll give you an example or some intuition on two of these, not all of them, but reuse and right sizing. So reuse, right? So we were talking to some folks at Microsoft, and what they told us was, you know, a lot of times when people think about AI inference, they think about people chatting with ChatGPT, Gemini, Claude, they're like writing their code, right? They want instant feedback. Within 100 milliseconds, within 200 milliseconds, they want that feedback. In reality, a lot of production services for inference don't need to return the results as quickly. In fact, what you're seeing on these plots is what we call batch percentage. So batch workloads are ones that can take 24 hours to respond with the results, and that's okay. So if you need to do like a lot of data processing, you like launch your scripts, you launch your queries, you submit them, you go to bed, next morning you wake up and your results are ready, right? You're training some model, that's batch workloads, right? You don't need the result in a minute, in a second, in 100 milliseconds. The batch percentage can actually be as high as 60% for some production services. If you have a lot of the slack, you don't need GPUs that are really, really good at doing high performance computing that return results really, really quickly. You can actually offload a lot of these tasks to the CPUs that are sitting idle. So that's kind of one of the intuitions. The other intuition is actually these CPUs they're not good at doing a ton of compute, but they have a lot of memory. A lot more memory than our GPUs. And so there's a lot of tasks within AI where you actually are more memory limited. You're limited in terms of the performance of the system because of the memory availability. either from the model perspective or even individual operators within a model. And so the analysis that you're seeing here is, we call this roofline methodology, but it's effectively saying that there are certain operators and parts of models that work well on CPUs. So if we can intelligently map them onto the idle hardware resources, we can also improve performance. Okay, I'm not going to go into the system diagram of our thing that we built to be able to exploit all these optimizations, and there were a lot more. So I'm going to skip over that. What I do want to show you is what comes off of these intuitions and these motivations. So in the x-axis here, you have carbon saving. On the y-axis, you have performance degradation compared to the performance optimal system that we can design. So we basically take the industry implementations, the best performance that we can get, that's on the y-axis. Higher is worse. So we want to be on the bottom right of this plot. The dots that you're seeing, so the energy optimal is, if we optimize for energy, what is the performance and the carbon saving we get? Melange is a cost optimized system. So if you had a designer that cared more about cost than performance, what would they design? And then Splitwise is a proposal from Microsoft that kind of balances energy and cost and performance a little bit. The different kind of tenets of environmental design, if we apply them onto the performance optimal design point, these are the points that we get. Reuse is an orange, right size is the blue star, and then reduce is the red star. So individually, these do a good job. They get like 20% carbon saving, very little amount of performance degradation. If you combine them, they do even better. We can get up to almost 50% carbon saving with only like a 2 to 3% performance degradation. The more interesting part almost comes in, these tenets actually apply to a diverse set of scenarios. So on the x-axis here, what we have are different types of input requirements. Online is something that needs to respond really quickly, right? That instant feedback. Offline is the batch workloads that we talked about. Long and short are what is the size of the task that has to happen. Is it a short task? Is it a long task? App A and App B are the two representative applications that we got in our from our collaborators at Microsoft. What we basically find is that by trading off these different tenets of environmental design, we consistently get 40 to 60% carbon savings. They just come from different sources depending on the use case. Okay, so this is our first kind of stab at how do we co-design the software and the hardware systems to improve sustainability. Now, the next question that we were really interested in was, a lot of what this work is motivated by is we have these really strict performance requirements that users are expecting for AI services, right? If you're talking to ChatGPT, Gemini, you really want to have as close to that instant feedback as possible. Maybe this will resonate with more of kind of like the HCI, the UX audience here. But we were curious about, are users willing to exchange quality of service for sustainability? So if we told people, look, are there aspects of this service that you're willing to degrade if we told you that you're doing good for the planet, that you're saving carbon, you're saving water, you're reducing e-waste in the world, right? Are you willing to do that? So the way that we thought about this is that there's three main aspects of a service. There's quality of the service, right? So if you have a video stream, what is the resolution, the quality of the AI results, and so on. Availability, can you arbitrarily log on at any time of the day and you know that the service is going to be available? And then response time, right? How quickly is that service responding? The users basically, when we did our user studies, they told us, there's no way that you're going to degrade quality. I want the best service possible. They said availability, I always want to have my services available, but response time was the one thing that they were okay trading off. And so our next step was basically looking at how much are people willing to exchange response time for sustainability. So this is a hypothetical example, right? Imagine that you have two users. One is a kind of high performance oriented user and they want the fast service. So they go on to your ChatGPT and they submit their query, and in the data center, it sees that and it says, okay, I need to respond within 400 milliseconds. It's a very urgent query. Right, this is actually a relaxed latency target. In reality, we think about 100 milliseconds and people start getting impatient. We're very impatient people. The second class of users are kind of these green users that say, okay, I can wait a little bit longer. It's okay, I'll go and I'll take a sip of my tea or whatever. As long as you tell me that you can save carbon footprint, right? And so here we're seeing that they're willing to exchange 100 milliseconds. We conducted this across different services, and kind of as expected, we found that for different services, people have different feelings. For Google search, for example, they didn't really want to degrade performance as much. Amazon e-commerce platform, same thing. Surprisingly, for AI services and ChatGPT, people were more willing. I think this is partly because people have this feeling that, oh, something so complex is happening, it's generating all this text, I'm okay waiting, I'll have a conversation with it afterwards, all this sort of stuff, right? And there's also all these articles coming out on the energy footprint, the data center cost, and the environmental impact, so maybe people are a little bit more cued into this. That's good for us because we can leverage this. So what we've been designing is this kind of eco-GPT system and interface. It looks a lot like ChatGPT, but it basically has this kind of pane on the side, or this kind of window on the side, that tells you how much energy and how much carbon and how much water you're saving by being okay with degrading the performance a little bit. And what we're starting to do is actually conduct these user studies to get more and more detailed into how much latency are people willing to trade off. And then the second part of this comes into, which is where my expertise mostly lie on the computer systems and architecture side, of how do we actually exploit the slack and the relaxation of the response time that people are giving us to more efficiently and more sustainably serve and process these requests. Oh yeah, I'm gonna basically start to conclude over here so that we have some time for discussion. But the path forward, we kind of started talking about using eco-feedback and using eco-feedback principles to open up the design of sustainable interfaces, right? I'll give you another example, right? So many times I go on Google search and I'm like looking at, I enter in my query and out pops this AI overview. And I don't want the AI overview. I just want to click on the next link. That AI overview is useless. It is wasted energy, wasted carbon. I wish there was a way to turn this off. I've started noticing recently that they don't always generate it. When they first released it, it was 100% of the time you would have this AI overview. So maybe they're trying to reduce their own cost to be able to do this. Another aspect that we're looking into is, for a lot of cloud customers, they're starting to ask this question of, depending on the amount of compute that I'm using, can you tell me how much carbon I'm responsible for? So we've been developing these software attribution mechanisms. Two of my students, Leo and Lisa, have been leading this on how do we dynamically tell at the software level how much carbon footprint different services, different applications are responsible for. The neat part about this problem was it's hard to do this fairly because there's so many dynamics in a data center. We actually go back to principles of economic game theory, and we apply principles of fair cost attribution to data center carbon emissions. Next part, this is the year of agentic AI or whatever. And so we've also been thinking about, well, how do we exploit hardware heterogeneity, diverse hardware platforms across different agents to more sustainably serve these end-to-end workflows. And then finally, to two last things. One is looking at more efficient models. So we have some work going on into diffusion language models, which can enable higher parallelism when you're generating queries or outputs. And then finally, looking at emerging technologies. So going beyond our traditional CMOS devices. And this is actually a partnership with some folks up at the Cornell Nanoscale facility in Ithaca, where they actually fabricate these devices. And they're interested in putting gas flow sensors and energy use sensors inside the Cornell fab. And we're using that data to basically create different backends for our ACT tool to be able to model different types of technologies and different devices that can be fabricated. Okay, I'm gonna stop there. Just a shout out to all my students that are actually doing all the research and all the work. But I'm sure they'd be happy to answer any questions. I'm happy to answer questions, and I'll pause there.
Thank you so much, Udit. This was it. I'm so glad that you were kind of bringing in all these examples of which, as a simple user myself, I have experienced, especially the Google AI, which has been really bothering me as well. But I didn't know that there will be so much sustainability impact behind it. But I'll open the floor for any questions people might have.
I have two questions for you, Judith. Thank you for your talk. It was really informative. Yeah, you hit it right on the head with the Google thing. This is about short. I'll start with the shorter question. Um, I was also getting really frustrated by it. You know, every time I search up something, even if it's like the word hello, it'll be like, oh, hello is this, blah blah blah, and it'll do this whole AI overview. And I'm like, there's at first they were probably just beta testing it, so they were just doing it for every single search. But there has to be some sort of like thing where they're storing the top, whatever, 100,000 searches, and they're just able to reuse the AI overview every time. I think that made me feel a little better. Like they must be doing that. So that's my first question is, do you think they're doing that, or is that a way they can save at their own energy costs? And then our second one was with the eco trade-offs for GPT. That was another thing that my startup studio or product studio group thought of. But we weren't looking at the time scale of like, milliseconds. I was thinking like more from my energy background, like utilities need load overnight. So we were like, okay, for researchers that have really heavy duty tasks, would they be willing to schedule their heavy duty task overnight? But the more I think about that, right, if ChatGPT is a global service, does that really matter? But because, it's always day for somebody. Did you guys think about that at all? That, you could offer longer time scales where it's like, oh, maybe there's a lull in the action, and then they can schedule more of the heavy duty loads.
Yeah, no, great question. So the first one, if I remember correctly, was the AI overview. So is Google caching the results or like pre-computing some of the stuff so that they don't have to generate it every time? Yes, I do expect that they're doing some level of this, right? They do this for search in general. So I hope at least that they're doing this for the AI overviews, otherwise it's a lot of cost. That being said, I think their goal is everybody has a Google profile, everybody has a Google account, right? Everybody's on Chrome and they have their own search history and their own personal experiences. And they're going to want to personalize the AI overviews that get generated. It's hard to pre-compute that, right? Or you have to pre-compute that for everybody, which is probably going to mean that you're over-computing in some sense. And so I think in the interim, caching and pre-computing works. In the long run, I don't know how well that will work in terms of saving the sustainability cost. I think the second question in terms of like the Eco GPT was looking at smaller time scales. Can we look at hours or like day versus night? So we haven't done this in the context of AI or like LLMs, but we have done this for other workloads in data centers. The tricky part is kind of what you mentioned, where data centers have a lot of upfront cost, right? And so data center operators are very much incentivized to use their resources 24/7. They don't want any downtime. And so what that implies is that yes, you could provide delay, but or like you could shift a workload from like day to night, but there's not going to be like only 10% utilization of the hardware resources at nighttime because something else is going to be going on. That being said, I kind of alluded to this, but power grids are very much constrained right now. And one of the things that they're not able to provide the raw power capacity that data centers are asking for. In particular, data centers are basically saying, I want a gigawatt of power 24/7, 365 days a year. Power grids are like, I can't give you that. But what they are willing to do is say, look, I'll actually give you double what you're asking for 99% of the time. As long as 1% of the time, or even 0.1% of the time, you go down to 500 megawatts. So a quarter of what you actually asked for. If you give that amount of flexibility, there's actually a lot of capacity built in. And that level of flexibility, the way that you get there, that kind of demand response flexibility is what we call it, is the same mechanisms that kind of the renewable energy workload shifting community and the sustainable systems researchers have been thinking about for a decade. So it's the same things, but the cost function just ends up being slightly different, which is kind of cool. But anyway, off topic a little bit.
Oh, thank you. That was that makes a lot of sense. Very helpful.
So, do you think that there will be labels, or are there any labels already if, as a maker, designer of physical objects and environments, I'm looking for products out there for graphics and designing? Are there already labels which we should be reading where they have explicitly told that how they are looking at sustainability in their product development, or there is no such labeling yet?
There's one or two labels right now. Like I think Energy Star is one of them. From a computing perspective, this is something that a lot of people are talking about. So there's an IEEE standardization body that's trying to figure out what is the standard for quantifying carbon emissions for devices, for AI, etc. I know that at the EU level, there's a lot of regulation that is currently being voted on, or is supposed to be voted on at the end of this year. I don't know what the state of it is. For consumer devices, there needs to be a carbon footprint label that is available for all devices that are sold in the EU. And that will tell you what the carbon footprint is, what the water footprint is, what the e-waste impact is. And there's a lot of data from the EU that at least European citizens are willing to make sustainability forward decisions. So they will pay like some premium for sustainable devices. I don't know if US citizens and like people here have the same behavior, but that's an open question. I guess what I'm trying to say is, if we look globally, yes, there is room for this, and there are examples that are already showing up. And even for computing devices, there are like sustainable devices, right? There's actually a startup, I think, in the EU that's doing like an eco GPT. And so I think there are business models that you could come up with here. It's just finding the right kind of consumer base and building off of that.
Yeah, I would love to pick your brain on like how as a consumer level we can kind of be more
Yeah,
aware of these because it's such a developing field that I hope if we get a good start at it, we might be better decision makers than not. So we don't want to train ourselves later, but like at least be aware of it from the beginning.
right. Yeah, I mean, I don't know how many people know, but if you have like an iPhone or Apple device, if you go to apple.com/environment, you scroll to the bottom,
Mm.
have a product environmental report for every single device that was ever made by Apple.
Mm.
So you can look up the life cycle carbon footprint of every one of your devices, what materials are used. Now, it is a company report, and they have had to amend certain things and change their methodology, but the data does exist.
Mm.
Um, and now the trouble with that is when you look at the reports and you see the value of like 100 kilograms of CO2, even to me, like that doesn't mean anything. Like I don't know if that is that small, is that a lot? How do I think about that?
Yeah.
And so finding ways to communicate what that means to people, I think is important, which is a little bit where our expertise stops.
Right. Anyone else had any questions? Feel free to um, bring it up now. If not, I want to thank you, Udit, for joining us today. And I'm hoping to share this because I know some of from the group were not able to join today. So this recording will be very helpful.
Of course, yes, and happy if folks want to email questions and want to chat more, happy to follow up offline as well.
Yeah.
Great.
Right.
Well, thanks everybody. Have a
Hey,
good Tuesday. Tuesday.
yes. Thank you. Thanks for being with us. All right.
Of course. Bye.
Bye, everyone.